Let's get a more general definition for acids and bases. We've talked about Arrhenius acids and bases. We've talked about Bronsted-Lowry acids and bases in terms of proton transfer. So now what we're going to do is we're going to talk about acids using the Lewis acids and bases definition. So whenever we start talking about Lewis acids and bases, the first thing we want to look at is what a coordinate covalent bond is. And this is whenever a bond is being formed between two species, but only one atom provides both the bonding electrons. So the electrons aren't being shared. There's only one species that's contributing it. So for instance, let's look at H2O. So if we have H2O and it were to gain a proton, so keep in mind a proton doesn't have any lone pairs of electrons. It doesn't have any electrons at all. This lone pair from the water will be shared with the hydrogen, and we'll end up with hydronium. So we can see right there that this is a coordinate covalent bond, and the electrons are only coming from the oxygen. Another example of this would be ammonia to form ammonium. So we have ammonia, which is NH3, plus a proton, and this would end up yielding the ammonium ion. So in this case, we could still technically use the Bronsted-Lowry definition for an acid or a base. So we would have the proton coming in, so would be the acid, and then the thing that's accepting the acid would be the one that's giving the pair of electrons. It's the electron pair donor. So it's easy to tell if there's a proton being transferred, but what if there's no protons being exchanged? And so that's where the Bronsted-Lowry definition falls short, and that's where we'll start to talk about the Lewis acids and bases definition. So a Lewis acid and base, a Lewis acid is one where you have an electron pair acceptor, and the Lewis base is where you have an electron pair donor. So for instance, here we have NH3 combining with BF3 to form this complex, and notice that there's a bond between the nitrogen and the boron. So the lone pair came only from the nitrogen. So that means that it was the electron pair donor. So this would be our Lewis base, and this would be our Lewis acid. And then one of the things that you may see in your textbook or on the internet is that the product is actually called a Lewis acid base adduct. And that's just so if you see that, you aren't surprised by that terminology. So let's go ahead and go back and look at that previous example of water gaining the proton and ammonia gaining the proton, and use this definition for Lewis acids and Lewis bases. Alright, so as we look at this, water, H2O, is donating this lone pair of electrons. It's providing the lone pair of electrons. So that would make water our Lewis base, and then since this proton is accepting the lone pair, we were calling this the proton, it's accepting that lone pair, this is what we would call our Lewis acid. Same thing down here with ammonia. We have ammonia with the lone pair on the nitrogen. It's providing that lone pair, so it's the electron pair donor, so this would be our Lewis base. And then the proton is accepting that lone pair, so this would be our Lewis acid. And then our products here, the hydronium and then the ammonium ions, those would be our Lewis acid base adducts. Let's go ahead and try a few more examples together. So one of the first things you want to do whenever you're faced with a more difficult example is you want to draw a Lewis structure so you can visually see where the electrons are coming from and where they're going. So here for CO2, you may recall it has a Lewis structure that looks like this. Looks like I got a couple more electrons there than I need. Then we have hydroxide. And that's going to go on to form HCO3-. So if we were to draw this Lewis structure out, you'd end up with something like this. Well, in this case, what we'd see, it looks like that this lone pair, or one of the lone pairs on the hydroxide, is coming in, forming a bond with carbon, and then one of the lone pairs that comes from the double bond is kicked out here. So since the hydroxide is the electron pair donor, what we'll end up seeing is that hydroxide is our Lewis base, and the CO2 is our Lewis acid. Let's try another example. So we have BOH3, and then all the oxygens will have 2 lone pairs on them, plus hydroxide. And then our resulting complex will look something like this. So as we look at this, we can try to trace what happened with the electrons. So we gained another hydroxide compared to what was initially present over here. So that means that the hydroxide, this lone pair came in. So it was the electron pair donor. So the hydroxide would be our Lewis base, and then BOH3 would be classified as our Lewis acid. So notice in all these cases, there's nothing that is donating or gaining a proton. Okay, so that's why we have to use this Lewis acid and base definition to predict these reactions and to describe them. Let's go ahead and try one more example together, then I'll leave you with one on your own. So here we have 6 cyanide ions, -1 charge. Then we have iron with a 3+ charge. And then this goes on to form some sort of iron cyanide complex. So this would be iron 3 cyanide. This will have some sort of octahedral arrangement with the cyanide. I'm not going to denote the triple bond, and just note that there's a lone pair on all of the nitrogens. And overall, there is a 3- charge. So here, all of these bonds, so we'd call the cyanide a ligand here, because we have a transition metal center. All of these bonds were formed by the donation of an electron pair from cyanide. So in this case, what we'll see is cyanide is our base, and iron is our acid. And then over here, the iron cyanide complex would be the Lewis acid base adduct. So let's go ahead and look at this example. I would urge you to try this on your own. So go ahead and pause the video. But then I'll go ahead and put the answer up. So what we can see here is the beryllium ended up gaining 2 more chlorides. So the lone pair came in and was donated from that. So whatever is donating the lone pair would be considered our base, and then this would be considered our acid. I hope this helps.